Welcome to Module 6 of our structural design class. Today our focus will be on the design of solid slab of one-story building in Excel template. So this is the general arrangement. So if you look at this arrangement, you notice that this panel 4 seems to be the most critical panel, followed by panel 1 and 7. So we are not going to design all the panels, but for a fresh graduate, you can actually, if you have the time, you can actually design all the panels. But for an experienced engineer, you just look at the most critical panel and just adopt and do the design. So we are going to adopt panel 4 as the most critically loaded panel. So let's just go straight to the okay, what is a solid slab? Solid slab is that slab that is either supported by 4 edges of adjacent beam or supported on 2 edge beam. So let's look at what this statement actually means. A solid slab is that slab that is either supported by 4 edges of adjacent beam or supported on 2 edge beam. So let's go back. So for a solid slab is that slab that is supported by 4 edges adjacent beam. So now this is the beam, this is another beam, and this is another beam, and this is another beam. So when we look at it, we have about 4 edges of beam, and this is the solid slab. So this slab is actually being supported by these 4 edges of beam. Then the next statement says that or supported on 2 edge beam, supported on 2 edge beam. So let's also look at that situation. Now this is our beam, this is our beam. So here we have the slab. So we can actually say that this is a simply supported slab. This is simply supported slab because the LX here is this other side. So this is a practical illustration of the definition of a solid slab. A solid slab is that slab that is either supported by 4 edges of adjacent beam or supported on 2 edge beam. Okay, so let's look at types of solid slab, types of reinforced concrete slab. We have solid slab, we have rib slab. Now rib slab is used for larger span or space in a situation where you have a span from maybe from 6 meter and above, maybe from 6 meter to 10 meter to 8 meter. You cannot use solid slab in such situation. And remember that the 8 meter, 6 meter, 10 meter I'm talking about here is actually the shorter span. I'm not talking about the longer span. So I'm talking about the shorter span of the slab. So when you have short span, then solid slab is not the option. So rather you go for rib slab, or you can go for flat slab. Though flat slab is solid slab beds, here we have a different construction method. So the way you construct a flat slab is quite different from the way you construct a solid slab. So we also have waffle slab, which is also when you need a larger space or span. So you can consider the use of waffle slab. Now things to consider in choosing solid slab. Okay, here you must understand that the span must be between 1 to 6 meter, else you adopt another type of slab. So please, when you are adopting a solid slab, make sure that your span, and when we are talking about span here, we are talking about the LX, that your LX, which is the shorter span, which is the shorter span must be must be between 1.0 to 6.0 meter, else you adopt another type of slab. Then number 2, when the span exceeds 6 meter, deflection is always problematic. So the moment you have a solid slab that the span is more than 6 meter, then checking deflection is always a problem. And in solid slab, shear is not generally considered in solid slab design, except where you have a concentrated load to predominate and the slab thickness is more than 200. So in solid slab, we don't really have problem with shear. But in a situation where you have a concentrated load that predominates the slab and the thickness is more than 200. Then another issue here is that having a thickness to be more than 200 mm is not economical. Remember that we are designing, number 1, for safety, and number 2, for economy. So when you have a solid slab thickness to be more than 200, then definitely that slab is not economical. Okay, so let's just go into the Excel design template. Okay, so this is the arrangement of a typical calculation sheet in template in Excel. Okay, now this is how a typical calculation sheet should look like. This is how it should look like. Now if you look at the first page, you has to do with design data. Here you define the intended use of the structure. So in our case it is residential. Then number 2, then the next information that you will see here immediately after the intended use of the structure will be the design life of structure, and we have explained this. Let's still go back and look at it again. Now for residential, we are using 50 years. Okay, so the code that is responsible for this is Eurocode. Some call it Eurocode 0, but it's just Eurocode. So let's look at it. Eurocode 1990. So table 2.1 is where you will find the indicative design working life of the structure. So design working life category. Now these are the categories of the design working life. Now our residential falls under category 4, where we have 50 years, building, structure, and other common structures. So this is where we get the information and also the indicative design working life of the structure. Okay, so I will be as fast as possible. The relevant material used for the analysis and design. So here you have to list out the different software that you are using for the design. If you are using Prota 2018, you have to list it out. If you are using Prota 2021, you have to also list it out here. If you are using robot analysis professional, you have to. If you are using SAP, you have to. Then if you are using Excel, in this case I said that Excel did 2016 for slab design. So I've been able to specify that I am using Excel 2016 for my slab design. Then relevant code used for design. So here Eurocode 1990, basic of structural design. Eurocode 1991, Eurocode 1, action on structures. Eurocode 2, concrete, design of reinforced concrete. Then BS 8500, durability requirement and concrete strength. Now we have material characteristic strength. So characteristic cube strength is 25 Newton per millimeter square. Then we have characteristic cylinder strength to be 0.8 cube strength. So our characteristic cube strength is 25. Then the cylinder strength is 20. So our design is based on cylinder strength. Remember that we are using the worst scenario to carry out our design. So ultimately mistake using the worst scenario to carry out the design. So in this case we are using 20 Newton per millimeter square. Okay, so and the reference is BS 8500 table A4 and A5. So let's look at it in BS 8500. So okay, so these are BS 8500 part 1. So here you have table A4, durability recommendation for reinforced pre-stressed element with an intended working life of at least 50 years. So under nominal cover, so we have comprehensive strength class, maximum water cement ratio, and minimum cement or combination content for normal weights concrete with 20 mm maximum aggregate. So here this is where the strength of our concrete falls: C20 25, C20 25. So we have said that C20 has to do with cylinder strength, while C25 has to do with cube strength. Okay, so our design is based on cylinder strength. Okay, I think so you define your characteristics yield strength for steel. In this case I'm using 410. So it depends on your location and it depends on your environment, but since I am in Nigeria, so in Nigeria we adopted 410 as the yield strength for steel. The density of concrete 24, unit weight of concrete, then unit weight of 225 block is 2.87. then we have roof loading 1.5. so we go through this. Okay, so here we have the 1R for all element fire resistance requirement. You can check this in this expression 4.1. So 1R for all elements. So you can see in table in Eurocode 2 part 1 2. Nominal cover C norm is 20. So how do we arrive at this 20? So when you come down, you will see a breakdown of how we arrive at this 20. So the minimum cover due to bond is equal to diameter of bar. So diameter, our assumed diameter of bar is 20 mm bar. So minimum cover due to environmental condition, assuming FC1 and using 2025 concrete. So here we have 20. So the code recommended 10 mm. So you can see this in table 4.1 in Eurocode 2. Then the allowance in design for deviation, assuming no measurement of cover. So we have this to be 10. So when you add this to this, you now have that our nominal cover C norm is equal to 20 mm. Okay, so therefore C norm is equal to this plus B to give us 20. Okay, so this design data. Bar uses 12 mm. Okay, so we go to action. Permanent action, which has to do with thickness of concrete, thickness of slab, safe weight of slab, screeding, finishes, rendering of service, then partitioner allowance. So in this case we are using 150 slab. So this is 150. This is 150. Okay, so this is 150. So the safe weight of the slab is 0.15 by 24. So density of concrete, so it give us 3.6. Then screeding we adopted 1.0. Then finishes rendering and service we adopted 0.6. Then partition allowance stroke wall load we adopted 2.87. This is the unit weight for 2 to 5 blocks. So our total dead load now become 8.07. Then the live load, which is variable, is 1.5. I think I've taken time to explain it, but let me still explain it again in Eurocode 1. Okay, so this is table 6.1, categories of use. Category A, specific use. This give us this define the usage or the specific use of the structure. So in this case we have residential area for domestic and residential activity. Then we have example, room in residential building and houses, bedroom and ward in hospital, bedroom in hotel and hostel, kitchen and toilet. Here table 6.1 does not give us the magnitude of the imposed load, but rather give us the description and the categories of these imposed load. So the table 6.2 gives us the magnitude of this load. So we come to table 6.2 under categories A, because our design falls under category A, area for domestic and residential activity. So here under category A, we look at it: floor, stair, balcony. So for the floor, one can adopt between 1.5 to 2.0 kilonewton per meter square as your imposed load. So in this case we are going to use 1.5 for the floor. So that is why we have this 1.5. Okay, then load combination and arrangement. So we are using ultimate load N. So design load will now be 1.35 GK plus 1.5 QK. So which, when you sum up, you have 13.145. So we approximate it to be 14 kilonewton per meter per run. Okay, analysis and design. Okay, so let's go back to the AutoCAD. So we are considering panel 4. So let's define our LX and our LY here. Note that the LX is the shorter span while the LY is the longer span. The LX is the shorter span while the LY is the longer span. So in this case, this is our LY 4925. These are LX. So you now see that our LX and LY does not really depend on the vertical and horizontal axis. So your LY can be on the horizontal axis and your LX can be on the vertical axis. So in this case we have our LY to be 4925. So this is panel 4. Okay, so we come here 4925, then LX is 4400. So the next thing is for us, and we change this to panel 4. So let's look at the edge condition. Let's look at the edge condition here so that we can effect the changes there. The edge condition here. So we have this continuous because there is a slab here. We have this continuous because there is a slab here. We have this one continuous because there is a slab here. But when you come to this other side, this side is discontinuous. So there is no continuation of slab at this point. So we can say that and this is short span, this is short span, so we can say that we have one short span discontinuous, we have one short span discontinuous. So here the most critical loaded panel slab, so we edit this to one short span, one short span, or one short edge, sorry please, one short edge, one short edge discontinuous, one short edge discontinuous. So when you look at the ratio of Ly over Lx, we have 1.1, and it is two-way spanning slab. Okay, what is a two-way spanning slab? Okay, a two-way spanning slab is when the ratio of Ly over Lx is less or equal to 2. So that slab can be regarded as a two-way spanning slab when the ratio of Ly over Lx is less or equal to 2. So if the ratio of Ly over Lx is greater than 2, so that slab is one-way spanning slab. Now what does this imply? What does this imply? Two-way spanning slab. It simply means that the main reinforcement is both on the y-axis and on the x-axis. The main reinforcement is both on the y-axis and on the x-axis. So which simply means that you will place your main reinforcement on this short span and also place the main reinforcement on this other span. So the two span axis, that is the Lx and the Ly, will have the main reinforcement. But in one-way spanning slab, you place the main reinforcement on the Lx, while the distribution bar will just be on the Ly. That distribution bar is always nominal, using 0.15% each. Okay, so we have been able to establish that. We have been able to establish that. So here we have that we have one short edge discontinuous. So let's effect the changes here. So you click here, you come to where you have line, so you come to this point and thicken this line and thicken this line. So here it has reflect the condition here, that will reflect the condition here. So the next thing we will do right now is to pick our moment coefficient that correspond to this edge condition. We pick our moment coefficient that correspond to this condition. Okay, so let's look at these slab cases. Let's see the one that correspond with what we have. So if you can see, this one correspond. This thing simply means that there is a continuous slab on this side, and there is a continuous slab on this other side, and there is a continuous slab here. But here there is no continuous slab. So we look at the ratio. The ratio is 1.1, and we have this that correspond with it. Okay, so span positive moment, so we have 0.033. so the moment coefficient here is 0.033. so you click on it. Then the next one for the H is 0.44. so you also input the value there, 0.44. and now go for the longer span, coefficient, still under this case. So for the mid span we have 0.28. For the mid span we have 0.28. So this is for the mid span, 0.28 for the mid span. Okay, then for the continuous edge we have 0.3. 0.3. Okay, so we have been able to select all the moment coefficients. So let's proceed with our design. Okay, here you calculate the effective depth of the slab. Effective depth is the slab thickness minus cover minus diameter of reinforcement. So here we have 150 as our slab depth, then our cover is 20, then the diameter of the main reinforcement is 12. So when you calculate this, you will have your effective depth as 124, and B is 1 meter slab section. So we designed solid slab for a meter section, unlike beam that we use the entire span. No, in slab we don't use the entire span, rather we pick a meter of it and do our design. So here we have flexure in span, bottom bar parallel to short span, Okay, so when we say bottom bar parallel to short span, what does it imply? So let's go back to the AutoCAD. Now this is the short span. So when we say that bottom bar parallel to short span, we are simply saying that the reinforcement that will be placed will be parallel to this short span, which is the first main reinforcement. So it will be parallel to this. So the moment coefficient that we use to design for this reinforcement parallel to short span is this one. 0.033. So let's go back and see how we can arrange that so that and mind you, it is a mid-span moment. So it's a mid-span moment coefficient. So here we have 0.0, I think 3, let me check again. Okay, 33. So this is the moment coefficient that we use to design for this reinforcement. Over the years of my practice, I've realized that most of our young engineers cannot really distinguish the particular moment coefficient that they use for the design of the mid-span moment and for the continuous phase. So I have to take time to explain this. So this is the moment coefficient that we use for the design of the main reinforcement on the x-axis. Okay, so that is why we have bottom bar parallel to short span. So we have, this is the moment coefficient, and this is the design load, and this is our LX, the short span length. And let me also say this: in slab design, irrespective of the axis that you are designing, whether you are designing for the long span or for the short span, we make use of the short span length. So we are going to adopt 4.4, which is the LX, throughout. Whether we are designing for mid-span, we are designing for continuous age, we are designing for long span, mid-span, we are going to use the LX, which is the shorter span. So from here you can see we calculate our K is M all over FCK BD squared. So here we make use of the 1 meter, the concrete, which is the cylinder strength that we use 20. Then this is our D, which is 1, 2. So we have K to be 0.029. Then we calculate for lever arm. Now, lever arm must not exceed 0.95. So if you calculate your lever arm and it exceeds 0.95, so you adopt 0.95. So in our case, our lever arm is more than 0.95, so we adopt 0.95. So our Z is 117.8 meter. Then our AS require, this is the area of reinforcement require. So in this case, this is the area of reinforcement require. Okay. So now in design, you provide something that is higher than what is required. So the area of reinforcement required for that short span is 213. So if you provide something that is higher than 213, it will be adequate. So in this case, we are using the spacing of 250. So the area of 250 spacing with 12 mm diameter is 452. So reinforcement is okay. Then the next one is top bar parallel to short span. Remember that this is the continuous edge. So we go back, top bar parallel to short span. So this is the top bar parallel to short span. So the reinforcement is going to be placed like this. That is for the support. Remember that if you draw the bending moment diagram of this, slab. Okay, let me see how I can draw the bending moment diagram of this slab, so that for you to see how it looks like. So let's draw the bending moment diagram of this, so that we can show where we have the hooking moment at the support and the sacking moment. So we have this and this. So we can just draw 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, here the moment is 0, and here also the moment is 0. So we have the hooking moment at this point, and we also have the hooking moment at this point. So let's see how we can just quickly do that, so that we know why we place the okay. Let me just, you don't mind my just trying to use it to explain. Okay, so here the moment is 0. There is no moment here because it is continuous edge. There is no moment here because it is continuous edge. But here we have moment because this is the continuous edge. So the next reinforcement, which is parallel to short span that we mentioned, is going to be placed here. So meaning that, let's go back to our drawing. So this is where that reinforcement is going to be placed. It's going to be placed at this point. While the first one that we designed, let me look at that. Okay, so it's going to be placed here parallel to short span and also on this direction. So parallel to short span, top reinforcement parallel to short span. So it's going to be placed here and also placed here. So we have So the reinforcement is going to be placed here and also placed here, while the first one that we designed was placed here. That is the short span reinforcement, bottom bar reinforcement parallel to short span. So that one is going to be placed here. Let me see. Let me just see how I can. This is just for illustration. Okay, this is just for illustration. This is just for illustration, please. So while this other one is going to be placed here, please, it will not extend up to this point. It won't extend up to this point. So it will stop somewhere here. It will stop somewhere here. This one will also stop somewhere here at about 0.3 of this span. 0.3 of this span. Okay, so we will also have the support reinforcement here also. Okay, so top bar parallel to short span. I think I've been able to explain that. So what is the moment coefficient for that? What is the moment coefficient for that? So let's look at the moment coefficient for that. Let's go back to the Excel. So let's go back to Excel. So the moment coefficient for that is 0.044. So that is the moment coefficient that we are using to design for that top bar parallel to short span. Parallel to short span. So let's 440, and we will have the same reinforcement here. So the coefficient is also here. Okay, so top bar parallel to short span. So we have 0.44 times this times 4.4. So the moment here is 11.93. This is continuous pitch. Continuous pitch. Or you can say support moment. This is support moment. Support moment. Okay, support moment. So we have 11.993. So the same procedure follows. So at the end of the day, we have the area of reinforcement required to be 284. So we still provide the area of 452 and our spacing to be 250 for consistency and uniformity. So you can see that the area of 452 is greater than 284. Okay, so we are done with the short span. So the next thing we will do is to consider the bottom bar parallel to long span. The bottom bar parallel to long span. Now in this case, our effective depth will no longer be 124, but rather it is going to be 112. Now how do we get with this 112? Remember that when we were calculating for the short span effective depth, we were dividing this by 2, but in this case now we are making use of the entire diameter of the main reinforcement, because this reinforcement, this long span reinforcement, is going to be placed on the second layer. It's going to be placed on the second layer. Okay, let me just see how I can quickly illustrate this. It's going to be placed on the second layer. So this is the short span. This is the short span. So this is how the reinforcement is arranged. So let's just quickly show how that reinforcement is being arranged. Okay, so this is how the reinforcement is being arranged for the shorter span. This is how it's being arranged at 2250. So the next reinforcement, which is parallel to long span, will be on this direction. Will be on this direction. Okay. Parallel to long span, so will be in the direction. So in section, this is what we are going to have. This is what we are going to have. This is what we will have. Understand? So this is what we have. So the first effective depth we were considering from half of this to where we have the top of the slab surface. So the next one we will consider this. So the whole of this is now being considered. We subtract the whole of this. That is why we have this 124 minus 12. So the new effective depth will now become 112 mm. So we now use for the midspan, the moment coefficient is 0.028. So for this long span, the moment coefficient that we are using for the design is 0.028. Okay, 0.028 for long span, for bottom bar parallel to long span. So we are using this. As usual, we calculating at the end of the day we have the area of reinforcement required to be 200 millimeter squares. So we provide 452 millimeter, which is higher than the required. Then the last one is the top bar parallel to long span. The same procedure, top bar parallel to long span. So this is top bar parallel to long span. Top bar parallel to long span. So the moment coefficient that we use for this design will now be 0.037. So these are the 4 moment coefficient that we use for the design. So remember that this moment coefficient is used for long span, bottom bar parallel to long span, while this one is used for top bar parallel to long span. This one is used for bottom bar parallel to short span, while this other one is used for top bar parallel to short span. Okay, so we are done with that. So for the top bar, the same thing. For the top bar we have the same thing. So we provide 250 and the area of reinforcement provided is 452. Then shade check. Now we have said earlier here that shade is not generally considered in solid slab design, except where you have a concentrated load to predominate and the slab thickness is more than 200. So here our slab thickness is just 150 and we don't have any concentrated load that predominates this panel. So here we don't need to check for shade. There's no need. So shear reinforcement solid slab is not necessary, except in the case of, so shear here is not important. Now, require percentage of tension reinforcement. Now, in solid slab we design only for tension reinforcement, that is simply reinforced, so we don't have doubly reinforced, which has to do with compression reinforcement. So in solid slab we design for simply reinforced. So require percentage of tension reinforcement is being calculated. Remember that we are using the short span, and we are using the short span, which is this, and the area for that short span is 213. Area of reinforcement required is 213. So this is A is required all over BD, and we have the percentage to be 0.17. Then we calculate for reference reinforced ratio, which is K. For structural system we have K to be 1.3. K to be 1.3. So this is where we have, remember, end span of continuous beam, or one-way continuous slab, or two-way slab continuous. So our K is 1.3. That's where we have the K. That's where we have the K. Then for required percentage of tension, tension and reference reinforcement ratio, which is real 0, while this one is real. So this code equation 7.16a say that if required percentage of tension real is less than or equal to reference reinforcement ratio, the Q real 0, then we adopt this formula. But if this is greater than this, then we adopt this formula. So in our case, when you look at this and this, you know that this one is greater than this, so we adopt this formula. And when we adopt this formula, we have this to be 12.8. So you can see this formula in Eurocode 1 equation 7.16a and equation 7.16b. Now, since required percentage of tension reinforcement real is this, then the slab is lightly stressed using the least value of 26 and 30. Okay, I further explain something here, that K is equal to 1.5 for interior span condition, so which give us this, which give us for lightly stress we have interior span of beam or one-way or two-way slab we have 30. Then for the end span of continuous slab we have 26. Now the code require that we should use least of this. Remember that our real is 0.17, which fall in these categories. So that is why we said that the concrete lightly stressed. So we are going to pick the least of these two values. That is why we have. That is why we are using 26. So we are going to use 26, because when you look at this slab is not completely an interior panel, and this slab is not also completely a simply supported, where you have n panel. So it's not. So it falls between the two, n span. continuous. So we are combining this, so we make use of the list of this for the design. Okay, so the value in table 7.4 is based on the assumption that the steel stress at critical section under the appropriate dead load is at serviceability limit state. So this is in table, this is table 7.4. This is table 7.4. 7.4. 7.4. So that is the assumption. So that is assumption under the appropriate design load as a beginning. So the stress is this, while the characteristic strength of concrete or steel is 500. Since we adopted a steel stress of 410, the value in 7. The value in 7.2. Sorry, please. The value is 7.2 table can be multiplied by 310. Conservatively, stress can now taken as this. So we multiply this by the steel stress that we use by the area of concrete required. So this can also give us 5 FYK times this, and from there we have this value. So we have this value, we have this, we are making use of this area of reinforcement required for the shutter span all over the area of reinforcement provided, which is 542. So we can see this in equation 7.17. So modification factor is equal to, so 310 divided by this stress, so we have 2.56. Therefore modified limit span to depth ratio now become, so this value for this 26 divided by this. Remember that we are making use of the list of this. So we are making use of the list of this. So here we divide 26 by this to have 66.5. Then the actual limit span to depth ratio is here. You now make use of the main span, which the main short span divided by the effective depth of the shorter span. So this is the actual, and you have 35 shorter span adopted for check, and required effective depth D is so this will now be the shorter span divided by this span modify limit span depth ratio. So you have 65.9 mm. The actual effective depth D is 125 mm. So you can see that deflection here is satisfied. Deflection here is satisfied. So that is actually the process of you designing the slab manually. Let me use that word manually, because the Excel template is just like you carrying out the design from the first principle, which is using the manual design approach. So I want to sincerely appreciate you. Thank you very much for giving me your time, and I believe that you have learned something. And I want to say that if you are not yet subscribed to our channel, please just do us a favor by clicking on the subscribe button. And if you have any comment, please feel free to drop it on the comment box, and I will endeavor to attend to your comment. Wherever that you don't have clarity, please just feel free to comment, and I will respond to your question appropriately. Thank you very much. I see you in module 7. Thank you. Bye bye.